Welcome to Lecture 7 on Power Series. This is moving on to section 11.9 in our book, Functions as Power Series. For those of you just tuning in, this series of lectures has been made for my Calc II students, and it really assumes a background in mathematics. In particular, it assumes you've been sitting in my Calc II course this whole semester, and we're about 3/4 through it. So if you haven't taken Calc II or haven't studied it, you may not follow this, but you're welcome to try. Okay, and so where are we right now? We've thought about power series quite a bit, right? And power series are a series that look like n equals something to infinity. Let's just call 0 to infinity of a n x to the n. This is a power series expanded around n equals 0. For the time being, let's look at a power series finding ways of writing power series expanded around n equals 0, x equals a equals 0, excuse me. And then we'll look at different a's about a equals 0. So that's x minus 0 to the n, right? And the first type of power series we're going to look at are the ones that can be really pretty quickly interpreted in terms of geometric series. And if you recall, for geometric series are a series of the form r to the n, and when the absolute value of r is less than 1, this is equal to 1 over 1 minus r. So we're going to look at functions that look like 1 over 1 minus r, or can be written at that, where r looks like some constant times x, right? Some constant times x, because then I'll be raising that constant times x to the n, and that's going to give us a power series. So this one here, this first one, is almost directly a geometric series. What is my r here? R is equal to just x, right? So as long as the absolute value of x is less than 1, this is equal to the sum n equals 0 to infinity of x to the n. Okay, so this power series is equal to this function as long as absolute value of x is less than 1. That means as long as x is in the interval from -1 to 1. Now, just a quick note of caution. Okay, so what we're saying is that these two functions are equal. If I plug in any x in this interval, this power series is going to sum to the same thing as I get here. So for instance, if I plug in x equals 1/2, here, if I plug in x equals 1/2, I get 1 over a half. That's 2, right? And if I sum up what I get when I plug in x equals 1/2 into this power series, it's going to converge to 2 as well. But that's only over this interval. If you notice, the natural domain of 1 over 1 minus x is all x not equal to 1. So there's a lot of things in the domain of this function that won't work for this power series, but in this interval, this is the power series for that. Okay. So now let's look at this other one. Now the other one can be written as 1 over 1 minus r for some r. And what is my r going to be? Well, let's rewrite that. That's 1 over 1 minus 2x, right? So r is equal to minus 2x. And as long as r, which is minus 2x, the absolute value of that's less than 1, then this is going to equal the sum n equals 0 to infinity of minus 2x to the n, which can be written as the sum n equals 0 to infinity of minus 2 to the n x to the n. It's better to write power series so you isolate the x. Now what's the interval? Well, the absolute value of minus 2x less than 1 is the same as saying -1 is less than 2x less than 1, right? Which is the same as saying -1/2 less than x less than 1/2. So the interval on which these two functions are equal is the interval from -1/2 to 1/2. And with geometric series, you don't have to worry about the endpoints because it won't converge at the endpoints. Okay. Now let's look at this other example here. This is a little bit different. Remember, we're looking for something that looks like 1 over 1 minus r first. And, well, that 3 I can factor out, right? I can write that as 3 times 1 over 1 plus x cubed. but we want 1 minus r, so I'm going to rewrite that as 3 times 1 over 1 minus x cubed. And here my r is equal to minus x cubed, right? And so as long as that is, the absolute value of that is less than 1, this can be written as 3 times the sum n equals 0 to infinity of minus x cubed to the n, which is 3 times the sum n equals 0 to infinity of minus 1 to the n, x cubed to the n, which is x to the 3n. Okay, and what interval is that? Well, this is the same as saying minus 1 is less than x cubed less than 1, or x is between the cube root of minus 1 and 1, which is just minus 1. So this is this. Okay, now you may be saying this isn't really a power series because this is x raised to 3n, not x raised to the n. Let me just point out that this is in fact a power series. It's just that some of the terms are 0. Oh, actually, let me write this in its fullest form. Let's distribute that 3/4 first, and that's going to be sum n equals 0 to infinity of negative 1 to the n times 3 x to the 3n. And that's really how you, that shows the an's here is negative 1 to the n times 3. Now, if you write a couple terms, we'll see this is a power series. At n equals 0, I get 3, just 3 times 1, 3. At n equals 1, I get minus 3x cubed, right? If n equals 2, I get plus 3x to the 6. If n equals 4, I get minus 3x to the 9th, and so on down the road. This is like a big polynomial. It's just that the x term, the x squared term, the x to the 4th term, the x to the 5th term, and so forth, the coefficients of those are all 0. So this is perfectly fine. Okay, so let's erase these and do a couple more in this thing here, a couple more examples. Okay, so I have a couple more examples up here. And remember, right now we're at the first stage of writing functions as power series, and we're looking for functions that can be sort of written in the form 1 over 1 minus r, where r looks like some constant times x, because then that's going to be some constant times x raised to a power, which is something we can deal with. Now this one I have here is not really in that form, but if you notice, I can factor an x cubed out, right? And I have 1 over 2 minus 3x to the 4th. And I still don't have it. I want 1 over 1 minus r, and I have a 2, not a 1. So let's factor out a 1/2 2. So I'm going to get x cubed over 2 times 1 over, when I factor out a 1/2, I have to factor it out of each term. And I have that. Now that is in this form. And my r is equal to what? R is equal to 3/2 x to the 4th. So this is going to equal x cubed over 2, n equals 0 to infinity of 3/2 x to the 4th to the n. And that, of course, is if the absolute value of this is less than 1, which is the same as saying negative 1's less than 3/2 x to the 4th less than 1, which is the same as saying negative 2/3 less than x to the 4th less than 2/3. So that means x to the 4th, well, x has got to be between the 4th root, negative the 4th root, and positive the 4th root. So that's going to be negative the 4th root of 2/3 x less than the 4th root of 2/3. So as long as I'm on that interval, this function is equal to this power series. And let's simplify that power series. That's going to be x cubed over 2 times the sum n equals 0 to infinity of 3 to the n over 2 to the n x to the 4n. And that can be rewritten as sum n equals 0 to infinity of, multiply the x cubed through, and I get x to the 4n plus 3. So that's a 4n plus 3. And that's going to be over 2 to the n times 2, which is 2 to the n plus 1. And again, that's if this function here is equal to this power series expanded around 0 if x is in that interval. Negative the fourth root of 2/3 to the, fourth root to the fourth root of 2/3. Okay, so let's do one more here. Now again, this is not quite in the right form either, but I can separate this. I can write this as 2 times 1 over 1 minus x plus x times 1 over 1 minus x. And both of these are in the right form with r equal to what? R equal to x, right? So as long as r, absolute value of r is less than 1, this can be written as 2 times the sum n equals 0 to infinity of x to the n plus x times the sum n equals 0 to infinity of x to the n. Now the interesting one in this is getting it in one series. Okay, so let's multiply through by the 2 and the x. So we're going to get sum n equals 0 to infinity of 2 x to the n plus sum n equals 0 to infinity of x to the n plus 1. Now the issue here is we want to add these together and factor out an x to the n, but I have an x to the n on one and an x to the n plus 1 in the other one. So I'm going to change the index of summation on this right one so that that changes to an x to the n, not an x to the n plus 1. So this is going to be n equals 0 to infinity of 2 times x to the n plus, well, to make that next to the n, well, when n equals 0 over here, I have a 1. So I'm going to start with n equals 1 here and just make that x to the n. Okay, now, again, we still can't add them because we don't match them up term by term. This first one's got a 0 term, the second one doesn't. But I'm going to take that 0 term out. So the 0th term there is 2 times x to the 0, which is just 2. So I get 2 plus sum n equals 1 to infinity 2x to the n plus sum n equals 1 to infinity x to the n. And look, now I can combine these two here and match them up term for term, right? The first, they've got the same terms and they've got the same x to the n, so I can factor the x to the n's out, and I get 2 plus the sum n equals 1 to infinity of 2x to the n plus x to the n is 3x to the n. And there is my power series, and that's for x from -1 to 1. Okay, again, let me iterate. Our original function is defined for all x not equal to 1, but it's equal to this power series expanded around 0 only for x between -1 and 1. Okay, this is a good place to stop. In the next example, in the next recording, we're going to look at integrating and differentiating things term by term.